Hi, everyone. My name is Justin Pflug. I'm a graduate student at the University of Washington, and today I'm going to be talking about some work we've been doing, taking a look at how to squeeze more accuracy out of our snow simulations using information about how snowpack is historically distributed in complex terrain. So to start with an example, we know that the heterogeneity of snowpack is very important. So to provide an example, we have two cases with identical snow volume, one homogeneously distributed and one more heterogeneous. And if we provide these two cases equal amounts of melt energy, we see there's a pretty dramatic difference about how snow evolves throughout the snow melt season for these two cases. Specifically, we see the heterogeneous case has a more gradual reduction in snow covered area as these shallower snow grid cells disappear at an earlier date. Yet these deeper snow grid cells persist much later into the snow melt season and therefore extend the snow melt season and provide water to things like stream flow much later than the homogeneous case. And of course, that's a very simple case, but these things scale up as we look at larger mountainous terrain where a variety of snow effects control the spatial distribution of snow and the spatial heterogeneity. Yet we still struggle to really capture the heterogeneity of snow in mountainous landscapes. So for example, as compared to observations here at 25-meter resolution in complex terrain of snow depth, we see that our model, while capturing mean snow depth fairly well, does not capture the heterogeneity very well. And this is partly due to model misrepresentations or not representing these effects, such as these that I've shown here. But it's also important to consider the fact that if we care from a modeling standpoint about, say, a snowdrift at 10-meter spatial resolution, and we have a model that can actually represent that, the computational requirements as we move to larger domains, watershed, whether it's mountainous, mountain range scale or continental scale, become pretty prohibitive computationally. It's also important to mention the fact that we may be limited on the first order by the accuracy of our model forcing. So for example, if we care once again about a fine scale snowdrift, do we even have the wind forcing accurate enough to push the wind where it actually belongs in this complex mountain terrain where wind patterns are very difficult to capture? For example, this was shown by Reynolds et al. In 2020 that showed dramatic difference between two simulations that actually allowed wind redistribution using two different wind products. So with this in mind, we really wanted to ask the question, how well can we actually reproduce peak snowpack using information that we have at our disposal, such as real-time satellite observations and historical information. In this case, the historical information being from snowpack reanalyses from the 80s to present day, and then also this information about snowfall spatial scaling, which I'll get into here briefly. I'll also take a look at these, how we think we can use this information in the Tuolumne River watershed, and I'll finish by talking about some future directions that we hope to take this work. So like I mentioned, we're going to be taking a look at the Tuolumne River watershed, specifically the upper Tuolumne, the digital elevation shown here. And we're going to be looking at this product called the Sierra Nevada Snow Reanalysis. So at a very, very basic level, this is developed by Margulis and group at UCLA. And very basically, it takes an ensemble of simulations using different model parameters and reweights those simulations to most closely match observations of snow cover changes in snow cover observed by satellite platforms such as Landsat. I would encourage you to go out and read more about this product. It's very interesting. But what we're seeing is that there's a high amount of accuracy in the Tuolumne River watershed. In fact, the coefficient of correlation between these reanalyses and LiDAR observations that we have at our disposal from peak snowpack midway through the melt season, typically the coefficient of correlation was ranged from 0.79 to 0.91. So great accuracy for our purposes. And we hope to use these historic snow patterns to actually scale our spatial snowfall. And this has been done by several folks, but we're going to be talking about this method employed by Vogli et al. In a 2016 paper. And what they did is they actually scaled snowfall using this concept of a pattern where they took snow depth at every XY grid cell and normalized by mean snow depth across the domain. So for example, in this region where we have LiDAR observations in the Tuolumne River watershed, we can see what this pattern looks like at two periods near peak snowpack timing in 2014 and 2016. And we see how that pattern is actually very similar from season to season. Then they actually took that pattern and multiplied by mean snowfall at every time t to generate snowfall map at every time t in every XY grid cell. So in other words, what they were doing was adjusting snowfall spatial heterogeneity as a proxy for processes not intended to being represented in the model. So these are processes like wind redistribution, preferential deposition, avalanching, and other effects not captured in the model. There are some assumptions with this, though. The first being that linear increases and decreases in snow depth are actually linearly related to increases and decreases in snowfall. But we know in space that snow density and snowmelt actually influences this relationship. So for example, given two grid cells with identical snow depth, a grid cell in an exposed region with much more dense snow and some snowmelt prior to an observation would require significantly more snowfall to achieve that snow depth than a grid cell in a shaded, colder region with less dense snow and no snowmelt. So what this really indicates to us is that we need to actually have a pattern that is generated by SWE, not snow depth, to neglect the spatial variation in density. And we need to have some estimate of snow melt or snow sublimation prior to using this pattern, so it can be adjusted by that amount. We also need information in real time about a historic period with similar snow distribution. So let's talk about that third bullet here in this next slide. In real time, we need to be able to go back in time and find a pattern that was very similar. So a similar pattern will have spatial increases and decreases in snow water equivalent that are aligned in space or well correlated. And it'll also have identical normalization. What I mean by normalization is that it needs to have a similar relationship between the standard deviation or the variability of SWE and the mean SWE. In this case, I'm representing that in this plot using the mean divided by the standard deviation or the inverse coefficient of variation. On the x-axis, what I'm showing is snow-covered area ranging from 0 to 100% across the Tuolumne River watershed. These dots then represent, in the reanalysis, the evolution of this relationship from peak snowpack throughout snowmelt. And while you see that this ratio between mean SWE and standard deviation SWE varies pretty dramatically from 0 to over 2, the trajectory is very repeatable. What I mean by this is that there's strong coherence between observations of the snow cover and the expected variability of snow across your domain. So using this suggests that we may be able to use information about snow cover in order to go back in time and find a pattern with similar repeatability. So let's test this. Let's say we're running a simulation in 2014, and we do have at our disposal a cloud-free Landsat observation of snow-covered area, shown here by the color bar, on the 5th of April, 2014, which is near peak snowpack. And we can actually use that distributed observation and go back in time and query the reanalysis to find a period with similar snow-covered area. And we found that on 30th of April, 1998, that pattern was correlated with 5th of April, 2014, with a coefficient of correlation of greater than 0.9. So a strong agreement. So in fact, we could actually use SWE on the 30th of April, 1988 to actually create a pattern to scale snowfall in 2014. So that's what I'm showing here. SWE at every XY grid cell normalized by mean SWE across the full Tuolumne domain. But of course, like I mentioned earlier, SWE at any point in time is not just a product of the snowfall that occurred at that grid cell, but it's also the overlapping effect from the cumulative snowfall at every grid cell minus the amount of snow that left via sublimation or snow melt. And of course, using this reanalysis, this pattern on 30th of April, 1998, we actually have a continuous estimate of snow evolution at every 90-meter grid cell using this reanalysis for that year. So we can actually correct this pattern using melt that happened at every single grid cell, as shown by this pattern here. And what you see is a pretty significant difference in patterns, specifically at these lower elevations. And of course, we actually do have a LiDAR observation at our disposal for water year 2014. So we can actually also create a pattern, as Vogeli et al. Did, using snow depth at every XY grid cell normalized by mean snow depth, as shown here. We then actually took these patterns and ran them through a snow model simulation using a model called Snow Model in water year 2014. Specifically, we performed these at 90-meter spatial resolution, forcing them at hourly time steps using meteorology and mean snowfall from WRF. The results on 7th of April 2014 are shown by these plots down here. ranging from 0 to about 2.7 meters of snow. And of course, this is on 7th of April 2014, and we do have a LiDAR observation at our disposal, so we can take a look at the accuracy of these 4 simulations. And I should also mention we performed a simulation without scaling snowfall using a pattern. So what I'm showing here is the accuracy of these simulations. The deeper greens represent model overaccumulation. The deeper purples represent model underaccumulation. Starting with the simulation that scaled snowfall using snow depth from 2014, we see a dramatic amount of overaccumulation at these upper elevations with some underaccumulation at these lower lying elevations. And this is really driven by the fact that especially these upper lying elevations were much less dense snow and therefore required less snowfall to achieve deeper snow depths. Instead, if we actually adjust 2014 snowfall pattern using a pattern from 1998, we see dramatic improvements in the performance, specifically at these upper elevations. And we can improve it even further by adjusting on a grid cell by grid cell level the amount of snow melt that happened prior to 30th of April 1998, especially at these lower lying elevations and these south facing slopes that received more melt energy. And there is a significantly better performance for this simulation as compared to the simulation that used no snowfall scaling and therefore had some issues with really capturing these effects like wind redistribution and specifically preferential deposition on the lee sides of these steep mountainous slopes. So with that in mind, we saw great performance in the Tuolumne River watershed, but we acknowledge that the Tuolumne River watershed does have very repeatable snow patterns from year to year. And this repeatability does vary depending on where you are in the California Sierra Nevada. So we would like to take this one step further in the future and take a look at other watersheds to see how applicable this method could be, perhaps from a water management standpoint. So with that, I'll wrap up. Our findings from this so far is that we're finding that at least in the Tuolumne River watershed, Landsat fractional snow covered area can be used as a criteria to actually go back in time, in real time, and select a historic pattern that we think may be most representative of real-time snow conditions. In simulations that we performed in order of accuracy, our most accurate simulation was the simulation scaling snowfall using a SWE pattern corrected by SWE losses from 1998. And this was significantly better than simulations that were scaling snowfall without using a pattern or scaling snowfall using a snow depth pattern, even if that snow depth pattern was from the same year as the simulation, in this case, water year 2014. And we acknowledge that, the Tuolumne River watershed does have very repeatable patterns. It appears like, at least, and we should be extending this work to more watersheds to take a look at the applicability to be able to actually scale snowfall to represent these effects that are not captured by models in the meantime for water management purposes. So I'll wrap up here. I would like to thank you for watching this. Please don't hesitate to reach out to me at my email located here at the bottom of this page. And I look forward to speaking with everyone during the open session. Thank you.